Hi everyone! My name is Maria Elise and I'm with the University of Rhode Island's Inner Space Center. Right now we're coming to you live from the main lab on Endeavour, which is currently located off the coast of Rhode Island. From now until September 6th, we're going to be streaming live with scheduled broadcasts at 11, 1, and 7. These will be broadcast on Rhode Island PBS and also online at innerspacecenter.org/RIREX. Right now, I'm joined by the director of the Inner Space Center, Dwight Coleman, and he's going to give us a recap of what's been going on and also an updated cruise plan on what we're going to be doing in the near future. Thanks for joining us, Dwight.
Great. Thanks, Maria Elise. Yes, I'm Dwight Coleman. I'm also the chief scientist on this research ship that we're on right now. So we're coming to you live from the research vessel Endeavour. We're just off of New Harbor of Block Island, and we moved here early this morning because we were over the site of the U-853, the U-boat that we want to feature during our broadcasts. But the wind was quite heavy this morning. It had switched during the night, and it came in from the northeast at about 25 knots, gusting to 25 knots. And so that was a little too much for us to handle with the deployment of the ROV and maneuvering of the ship around the U-boat. So what we decided to do is come over to the lee side of Block Island, which is off of New Harbor. We're on the west side of Block Island now, a little more protected from the wind. And so we just actually completed a live dive on a shipwreck. So we had quite a busy morning. It's been very successful. We got our ROV working. We had some technical challenges early on in the week when we were experiencing some electrical problems and a ground fault associated with operation of the ROV. And so we had those technical challenges, but we overcame them, and our engineering team basically did a lot of work to get things ready, and we had a very successful dive this morning. So the research vessel Endeavour is part of the Graduate School of Oceanography, where I work. The Inner Space Center is part of the GSO. All broadcasts are really due to this telepresence technology that we employ on the ship. So we have a satellite telecommunication system on board. We're broadcasting via satellite, and we had a high bandwidth internet connection to the ship through the Inner Space Center. So that's this model of telepresence that we're using to broadcast live. And what we can do is when the ROV is diving, we can have all that video streaming live to the internet, streaming live to schools around Rhode Island. We actually have a Rhode Island teacher on board with us who's been communicating with her classroom during this week, and basically connect everyone via the internet, and also build on our partnership with Rhode Island PBS to do these broadcasts. So this is the telepresence technology that we're using. We have the ROV technology that we use to dive on these shipwrecks, and we're working closely with the URI Department of Ocean Engineering. Steve Licht and two of his graduate students are the pilots that keep the ROV working, and they control the ROV while we're doing those dives. So you'll actually be introduced to Stephen Licht later in the broadcast. We're also here with Tom Rossby and Cody Fisher. Tom is a physical oceanographer with the Graduate School of Oceanography, and Cody is an electrical engineer, the chair of the electrical engineering department at URI, and they've developed some new technology that they're going to talk about later in the broadcast too. So this is a very multidisciplinary crew out here doing lots of different research. We always have to have contingency plans in case of weather or in case of conditions or technical challenges with the vehicle systems, and always come up with new things to do. So Tom Rossby and Cody will talk about their project and the other things that we do in addition to exploring the shipwrecks with ROVs. So that's pretty much what we're up to. Over the next couple of days, the weather will improve, we know. We'll go back to the U-boat either late tonight or tomorrow morning, and hopefully get some dives in on Saturday on the U-boat U-853. So that's what we'll be doing.
Excellent. Thanks so much, Dwight. Sure. I think now we're going to bring in Tom Rossby and Shannon Donovan. I guess we're moving over here. So why don't you both take a minute or two to introduce yourselves and tell us why you're here.
Okay. Yeah. Okay. My name is Tom Rossby. I am a physical oceanographer at the Graduate School of Oceanography. My activities over the years have been to study ocean currents, and the way we do that for many years has been to put out neutrally buoyant floats, which drift in the ocean, but they're at depth, so we can't use radio navigation to track them. Instead, we use acoustic navigation in the ocean. And what we're doing here is testing this acoustic navigational technique towards an entirely new technology that has been developed here at the university, namely to track fish underwater with tiny little tags called fish tags, or archival fish tags, that is, they record the data inside. What I'm going to do here first is talk just a little bit about the sound source technology, that is the way we set up the acoustic navigation. Let me first Shannon introduce herself.
So, hello, my name is Shannon Donovan. I'm a science teacher at Scituate High School in Rhode Island, and I am thrilled to be a part of this adventure, this research cruise. This is my first time being on a research vessel, and being among great minds like Dr. Tom here. For my teacher colleagues back on shore, this is a really great demo that can be connected with a lot of the science standards that we need to address. In particular, looking at waveforms and resonance, this is a really super demo, so I'm really excited we have a chance to do this. So you want to instruct me?
Yeah. Yes. What this is a demo of the way we generate the sound in the ocean. And the instrument that we actually have to make the sound, I don't know if we're able to show that picture of the sound source. But in any event, it's an aluminum tube about as long as I am tall. And inside that aluminum tube, there we are, we have the picture there. Inside that aluminum tube there, in the middle of it sits a little black sphere, which is a speaker. And that speaker is like a balloon that expands and contracts radially at the frequency of interest, which in our case is about 260 hertz. And that sound inside this, it's a pressure waves, which then resonate inside the pipe, and so that we can couple that energy very effectively into the ocean. It's like a musical instrument, an organ pipe, or a clarinet. You set up these standing waves. What we're going to do is demonstrate how that pipe works. So, Shannon,
For my friends at Home Depot, I will be coming to get a piece of this very shortly.
Okay, what we're going to... I need a third hand here, I think. So, yeah, Alicia, you could hold that. And then what I'm going to do is, you all have probably one of these things. It's an iPhone. And on the iPhone, I have a little app called Tone Generator. And so if I turn it on, you'll hear it make a tone. So now I can dial down. Whoa, I didn't want to go the other way. I wanted to go down to a low frequency. So I'm going down to about 130 hertz, or 130 cycles per second, right about there.
Hopefully you can hear that. I know my phone wasn't picking it up earlier, but...
So that's what that sounds like. So now I'm going to turn it off. So it's off. And I'm going to slide it into this pipe. So it's about halfway down the pipe. And now I'm going to turn it on again. Doesn't want to turn on now.
Ooh. It did. Ooh.
Now that is very strange. This is not part of the demonstration.
Murphy's Law. Woo!
There you go. Can you hear that? Can anybody hear that? Really I'm hard of hearing, but I can hear too. Okay. Now I turned it off. So I'm going to do one more thing. So this sets up standing waves inside the pipe. The pressure. Yeah.
But that only works because you figured out the frequency of this tube, and you can adjust the frequency of that?
Yeah, that's right.
You want to do that? Yeah. Show?
Okay. So we'll turn this on again. I don't know why it's a little... This worked so nicely earlier, didn't it? Oops. There we go. Now it's working. But now I can change the frequency. I can go down a little bit.
See how quiet it gets? Because then the frequency doesn't match.
Doesn't match.
No longer matches the resonant frequency of the tube.
So now I go up. Woo! And I go up higher, and it doesn't work as well. So there's a natural frequency for this to operate at. Okay? All right. So now I have resonance. And this is setting up, if you hold your hand here, you can actually hear the air rushing in and out, which is pretty neat. So at great risk, I'm going to turn this off for a second. And I'm going to turn on...
This is to show that sound waves are pressure waves.
Open flames on a ship are not allowed. But I did ask the old man for permission. The old man, by the way, is an affectionate way of referring to the skipper on the ship. He is the man in charge. And I need his permission to turn on this thing. So now I have a flame. I don't know know why it's not going out, but you can see it flickering. It's supposed to go out. It did this morning when we did this, but you can see the flame flickering anyway. That means the air is rushing in and out. And there we go. Boop. So anyway, that's the way we generate the signals. And these signals at low frequencies in the ocean, and they're not even very loud. They're not much louder than a good loudspeaker in your living room. That signal can propagate or spread out over something like 1,000 kilometers. So by having a sound source like this in several different locations, we provide what's called an underwater navigation system. And the floats that we have or the fish tags that we have can then know where they are as a function of time.
So this is a really great demonstration that teachers can do in the classroom. And so thank you for teaching me how to do this. And they sell other sizes, so I could get other diameter and test some other frequencies. We can have a sonotube orchestra. All right. So I'm going to turn it back to Maria Elise, who is, I think, going to tell us a little bit more about the next component of this system. Thanks.
Thank you.
I am, and I actually would like to bring Cody Fisher, who also is working on this project. Here he comes.
Hello, Maria. How are you?
Hi, I'm excellent. Why don't you start by telling us a little bit about yourself, how you got into your field, and maybe how this project was conceived?
Sure. My name is Cody Fisher. I'm an electrical engineer by training. I'm also in my 5th year as a chair of the Department of Electrical Grid and Biomedical Engineering. And as you might have guessed by hearing me speaking now, I didn't grow up here. I grew up in a landlocked country in Europe, Switzerland. I have to say, though, I was growing up at a big lake, so basically water and me have always mixed quite well. And I'm still doing it now. I'm an avid swimmer. And I started to get in touch with Tom probably about something like 10 years ago, where we started to work on our cool little things that we call our sonar receivers.
Can you tell us how they work?
Yes, you have just had the demo with the big pipe that creates the sound. Well, our job is to create a circuit that can detect and identify the type of sound in here. As you might surmise, there is a lot of sound in the water, in the ocean, boats, and animals create sound as well. And our job was to be able to discriminate between the sound that's there that we don't want to listen to and the sound we want to listen to. To do that, we know the type of sound signature that has been created by Tom's source. And what we do is we store a duplicate of this sound signature digitized in a computer chip. And the receiver then listens to and identifies the incoming sound. And whenever we have a match, it identifies the arrival time of the sound signature. And by knowing the time of travel between the source of the sound and the position of the receiver, and knowing the speed of sound, we can detect the distance to the sound source. And in doing that, with multiple sources, we can identify the position of the receiver underwater. It should be noted that a GPS system does the same thing, probably even more precisely, but it doesn't do it underwater because, unfortunately, the GPS radio transmissions do not penetrate the water. So our system is basically capable of positioning objects in the water, be it fish, any kind of animal, or floats, all kinds of floats.
So why are you doing this? Are there other applications for this technology as well?
Well, I think I shouldn't say that. Part of it is it's fun. But, of course, applications are any vehicle that's underwater, you would like to know its exact position. And having a tiny receiver, which operates with a very tiny power budget, is very, very handy. To give you an idea about the power that we consume here, our chip runs with a power that is about 2 million times less than the power of a typical light bulb. And therefore, a tiny watch battery can operate this device for about 2 years.
So we had a question come in on our live chat, and the question is, does each fish chip have a different acoustical ping?
The answer is no. We have not too many sound sources because they are relatively bulky, big, and also costly. So therefore, we have to listen to one or two different types of signatures only. In this case, what we have currently, we have two signatures. We can have what we call a frequency upsweep, going from low to high frequency, and we can also detect at the same time the opposite, going from high frequencies to low frequencies. But potentially you could do that, but it probably would be a costly thing to do.
So you did a test of your equipment here during the cruise. Can you walk us through the steps of that experiment?
Well, the first step was to lower our sound source in the water, and you have seen a picture of it. It's very big, so you can't actually lift it around. It's probably weighing something like 150 kilograms, 300 pounds. Is that correct? Ballpark. So that was the first thing, to lower that and bring it to a depth of, in our experiment, we used about 40 meters underwater. And then used the Endeavour to steam away at certain distances. And we have these pods that I'm holding here in my hand. Maybe you can hold my microphone here. These are basically about 5 times bigger than the final fish tag will be. Obviously, this would be a tag for a whale only. Wouldn't be good for a flounder. But inside is our electronics, and the electronics is basically as small as it will be for the fish tag. I'll try to open this one up here. It's a little bit jammed. And show you what the circuit board looks like. Probably you can see it here. On this board, which we call a printed circuit board, we have our fish tag is inside this microchip here. This is a fairly large package, but the chip itself is only 1.5 by 1.5 millimeters, which is about a little bit 1/16 of an inch, something like this. And this chip does detect the sound signatures, the arrival times, it measures the water pressure, and it measures temperature. And all that is then stored in extra memory, which we call non-volatile memory, which are, in this case, tiny little things you can see on the side here. If I hold them here, these little dots here. And that's where the memory stores the information, and since they're non-volatile, that means they do not lose memory, even if you run out of power. And ultimately, to read the memory, one has to retrieve the device, the fish tag itself. And of course, in that case, we depend on fishermen to catch the fish and being nice enough to give us the tags back.
All right, well, we had a question come in about how large the tags are, but I think, did you answer that?
Yeah, well, the exact size of the tag is, it's 2.5 centimeters, which is 1 inch long, and about half an inch in diameter, which, as I said, is just about 8 times less than this. Is about 8 inches here, and the real one will be 1 inch and half an inch in diameter.
So what kind of fish do you put these tags on?
Well, typically fish that are of commercial interest would be cod, flounder, salmon, something like that. But potentially you can attach it to anything you want underwater, as long as you have a chance to retrieve it.
So there's no specific species that you like to use for this?
No, absolutely not.
So how long do the tags last?
They are expected to run for about 2 years, and that is the lifetime of the batteries.
And you said this has to be brought back in order for you to retrieve the data from it. So if you lose it, you lose your data?
That is exactly correct, and that's most unfortunate. We would like to have a tag that will be able to transmit. In order to do that, you need, of course, much more power. I mean, the possibility would be to have a tag that at the end of its lifespan would surface, and having a transmitter that would send the data to a satellite. That can be done, and plan is to do something like that in the near future, but it does require more power and a larger package.
So how many fish do you release at a time with these tags?
Again, it's a cost factor. Obviously, the tags have a certain price tag. We don't know the exact price of it, but we would like to use as many as possible, but practically you talk about maybe a few hundred.
And why is it important to understand the movements of these fish?
Well, I guess fish biologists and fishermen have an interest to learn more about certain species in terms of habitat, feeding grounds, and what else, where they are. And of course, having more information collected by these tags will give them a little bit more of a complete picture.
Okay. And how was this project conceived?
Well, I don't even know exactly when it started out. It was at least some 10 years ago. Was a colleague of ours, Conrad Rexick from Fisheries at URI, and Tom Rossby, and somehow we got in touch and we talked to each other, and then we thought, well, that's a neat thing, we could do it much smaller, and hopefully with a power budget that lasts for about 2 years, and the cost tag that will be commercially viable.
So what kind of technologies are critical for this sort of experiment on the small scale?
Well, other than the sound technology that we have used, it is, of course, microelectronics, which makes it possible to build devices, circuits, that have tens of thousands, actually I should say tens of millions of devices on a tiny piece of silicon. And they are relatively cost effective if you can produce them in large numbers. And we are lucky in this case that we can fabricate with some support from the semiconductor industry, because producing chips with a small scale would be very, very costly, because typically you buy wafer scale numbers of chips, which means thousands, tens of thousands. In this case, we have hundreds only, but they give us a rebate on that, which otherwise we wouldn't be able to afford it.
Well, thank you so much for joining us today. We really enjoyed hearing about your background and about your experiment, and I think we're going to move on to the next guest.
Thank you very much.
Thank you. Our next guest is Mike Brennan, who is a marine archaeologist for the Ocean Exploration Trust. Welcome to the show. Why don't you tell us a little bit about yourself and what you're interested in?
Sure. Hey, I'm Brennan. I'm a marine archaeologist with the Ocean Exploration Trust and the Nautilus exploration program. So I'm out here as the archaeologist for this expedition where we look at shipwrecks off Rhode Island. We were just diving on a shipwreck of the Montana, which sank where we were just west of Block Island. We're in the lee here, so just west of Block Island, and we came across. It's a wreck that's on the chart. So we were looking for something shallow in this area to dive on because we're experiencing a high winds, so we took shelter here and we found this wreck to dive on. It sank in 1907 when it was being towed. It was a wooden ship with a cargo of coal. I don't actually know why it was being towed, but it wasn't able to make it. I think it sank in a gale, I think, during that time when it foundered. So we went down and we saw what we think might have been some sort of capstan or anchor chain, and we saw the mast, which was still standing up, but it was bent over. So there's metal parts of the wreck, but most of it was wooden. We saw the outline of the hull in our sonar, and it was primarily a cargo of coal, so we saw some little bits of coal hanging around.
Awesome. I think there was another thing we saw there that it looked large, and I have no idea what it was, but I think you were watching. Did you have any guesses on that for anyone who may have been watching the live feed?
Oh, we saw what looked to be some sort of large squarish block. I'm not sure what it may have been ballast. It may have been something like that. I'm not actually sure what that was. We didn't get a very good look at it. We got blown off with the winds, and we were working our way back, but had to come up. So I don't think we got a second look at that.
Okay, well, thank you, Mike. I think we're going to switch gears again and talk a little bit more about the ROVs and the engineers we have here. So thank you for joining us. So this is Steve Licht. He's from the Ocean Engineering Department at URI, and he has two graduate students here with them. One is piloting the ROV, and the other one is doing...
He's actually managing the tether. So the way the ship is set up right now, it doesn't have what we call dynamic positioning, which means that you can't sort of automatically set and forget a location for the ship on the surface of the ocean. So it moves back and forth, sometimes up to 50 or 100 meters. So we need Matt Perkins on the deck to pay out the tether so that the ship doesn't drag the ROV around. And when the ship starts coming back over the ROV, he pulls in the tether, and as he moves away, he lets it out again. So Matt Perkins' job is to make sure that tether doesn't hang us up. Jordan Kirby, who's my other student here, is the pilot for the ROV. So if you ever see him sitting in our sort of pilot's chair, he has a joystick console in front of him with a lot of buttons, a couple of dials, and a variety of other things, some of which I know what they do and some of which I don't. I'm kind of hampered because I didn't grow up playing a lot of video games. So what I've discovered is that I like to let my graduate students, who are significantly younger than I am and have played a lot of Grand Theft Auto, I guess, they really know what they're doing when they pilot the vehicle. My role is sort of to sit back and make sure that the tether is moving in and out properly, that the ship is on the right heading, that the currents and the wind aren't driving us off station, and finally kind of trying to help Jordan to figure out where the wreck is. The way we do that is once we're down at the bottom with the ROV and we're moving around on the bottom, typically we'll either just sit down on the bottom and wait as our sonar, which is a ranging, sound ranging, which can look 360 all around the vehicle. And wherever you pick up a response, you get a really high response, there's a good chance there's something solid there. That, for instance, might be a shipwreck or so. And then we orient ourselves and drive in that direction. Of course, as all this is going on, there's 6 different variables that you have to keep track of: where the wind is, where the current is, how much tether is out, whether they're sailboats or motorboats driving around the Endeavor, which might hit our tether, and also whether we're going to crash into the wreck or not. So we need to keep track of all those things as we go along.
So we've had some technical issues over the past couple days, and I know you guys have been working very hard to fix them. Can you tell us a little bit about what happened?
Sure. Well, I should say that I actually originally got into this business because when I was an undergraduate, my senior year, I went to a talk by a fellow who'd done a lot of research in the Mediterranean. And he showed us all these great pictures of boats and blue seas and lovely islands. And I thought, this seems great. It's like a vacation. It's a holiday. I'll sign on for this. What it turns out to be, though, is that when you put in this incredibly complicated platform, you have a remotely operated vehicle that has hydraulic systems, electrical systems, mechanical systems, video, all down the line. There are literally hundreds of ways that things could break, could wear out, could get set the wrong way. You might have a software fault. So most of the time you spend as an ROV operator, and indeed even as an ROV pilot, you spend less time sitting in that chair piloting the vehicle around than you do crowding around the vehicle trying to figure out what the latest thing that went wrong was that's stopping you from dying. So we've had troubles, for instance, on this cruise where electricity, when the current runs down to the vehicle, some of it actually gets leaked out into the ocean. Seawater is highly conductive, so we get these current leaks, and we've spent a lot of time sorting out where they're coming from. We have 3 major systems on our ROV. There's an arm with kind of a claw on it, a grabber. There's a separate system that runs most of the cameras, and then there's the main system for the vehicle that runs the thrusters and the main camera. So if we have a fault in one of these places, it could be any of 200 things. First, what we have to do is we have to isolate that. So we shut off one system, put the vehicle in the water, see if we still have the problem. Bring it back, shut off another system, stick it back in the water, see if we still have the problems. And that way you can say, all right, well, it's not those 600 things, and it's probably not those 300 things, but it might be something in this general vicinity. And then you spend a lot of time testing and checking before you go in the water again. What's interesting about ROV ops is it always seems to be that you spend a couple of days, 3 or 4 days, just trying to get the thing running, and all of a sudden you get into this nice mode where the vehicle's running, everything's working, and you can just put it down in the water and dive over and over again. That's what we're hoping to get to, and I think we're pretty close to that right now.
So we have one last question for you, and this student is wondering what they can do in high school to get on the right path to do what you do.
Sure. Well, in high school there are a lot of robotics competitions that can get you involved in doing hands-on work, building robots, and understanding how hard not only is it to build the robot, but then to get it to do the thing that you want it to do. Because it's typically driven by software, so you need you write the software thinking, I know exactly what it's going to do, and then the robot goes off and it does something completely different. So you go back to the drawing board and you figure out why that is. The other thing I would say is definitely programming. If you can take any kind of programming course or teach yourself any one of the many popular programming languages out there, that's going to set you way ahead when you start wanting to research robotics, because so much of it is software.
I think maybe we have time for one more question. Nope. All right, well, thank you so much for joining us.
My pleasure.
Thank you to all the guests for joining me here today and all of our viewers at home. I want to remind you that we'll be continuing to stream live on interspacecenter.org/RIREX with scheduled broadcasts at 11, 1, and 7, so our next show today is at 7. If you're curious about how you could ask questions of the scientists, visit our website at interspacecenter.org/RIREX. Thanks for joining us, and continue to explore with us.